All right. Thanks everyone for coming for our first in-person AI/ML seminar in a long while. So yeah, we're extremely excited to have Sunipa here. She's currently a research scientist at Google for the past month or so. Pretty new there. Before that, she was working with Kaiwei on a NSF Computational Innovation Fellow postdoc. And before that, she did her PhD in University of Utah. She's done a lot of work in fairness and NLP and interpretability and looking at it from sort of directions that other people aren't even thinking about. So I'm pretty excited to hear the stuff she's going to be talking about today. So yeah, let's welcome her.
Thank you so much for the very kind introduction and for having me here for my first in-person talk in about 2 years now. So please bear with me as I try to figure this out. I have never done this with a mask on, so if I'm muffled, please stop me. If you have any questions, feel free to stop me. So today I'll talk about some of my work towards building language technologies that are inclusive, that are fair, and that are socially aware. Now we'll go through what each of these terms could imply slowly over the course of this talk. But let's first think about language models, or whether we call them large language models or foundation models or the many names that have come up since. They are all these really large distributed representations which have this capability of compressing a large amount of information into relatively few dimensions and capturing a lot of meaning of the underlying language and being very applicable to a wide range of tasks and applications, even beyond NLP. But what we have gained in efficiency, we have lost in interpretability, because we do not really know what information really gets captured where in the embedding space. So what this means is we no longer have the feature to dimension mapping that we could have with explicit representations. And this has very unique effects on the representations overall. Most unique and harmful of which potentially is that of the fact that biases get captured in different ways across the embedding space. So what bias refers to here is this sort of preferential association between different groups of words or text excerpts in ways that different pejorative connotations or stereotypes are learned and expressed in these language models. So these could be about identities of people or protected demographic attributes like gender, race, sexuality, ethnicity, nationality, and more. It's a little more tangible to think about this bias in terms of the actual harms experienced by people. And this harm can be categorized into two broad categories, that of representational and allocational harm. Allocational harm is more intuitive because it relates very closely to experienced harms or experiences themselves of people. So for example, it could be about unfair treatment of people or unfair distribution of resources. So if we have, say, a resume sorter, which looks at names of people and sort of identifies or assumes somebody's gender or their ethnicity and uses that to drive the decision-making process rather than using the capability or other qualifications, then that can be considered an allocational harm. Representational harm, on the other hand, is a lot more subtle. It's a lot less intuitive like allocational harm. But let's try and think about it in terms of context-free embeddings because they're easier to visualize. So let's say we have these high-dimensional vectors, and they have these representations such that different similarities or different differences between groups are propagated, and we can find clusters such that stereotypes or generalizations about entire communities that are negative are propagated, then that is the representational harm. While this is a representational harm, what we will see slowly is that this can actually also lead to tangible allocational harm. So for example, what we have known for a while now is that in these representations, there are these disparate sort of associations such that word groups are like very differently associated with different identities. So we have known for a while that, for example, doctor is more associated with masculine, and like if you might have dancer or nurse more associated to females. But that's not the only extent of it. It actually translates into real world applications, as has been seen with one of those applications called Genderify, which had tried to assume gender from name. And then if you had doctor so-and-so, it would always predict masculine. Now, if we break this down into actual tasks that we would see in NLP, we see something very similar. So for example, let's take the task of NLI, and we will go through this measure more carefully later. But what we have here is a pair of sentences, a premise and a hypothesis. And the task is, given the premise, is the hypothesis entailed, contradicted, or neutral to the premise? Now, in the premise, we have the doctor bought a bagel, and nowhere in the premise is the gender mentioned. So if we got a human to annotate this sentence pair, what we would have is a neutral categorization. What we have instead, using glove representations and the decomposable attention model for NLI, we find that this is a contradiction with a very high probability. So this is telling us that the gender was somewhat assumed stereotypically by the model during this prediction. So we will go through this particular measure in more detail later, but let's take a more underspecified example. Here we have a sentence, the doctor notified the nurse that she would be leaving early. Here, the pronoun she could actually relate to both doctor and nurse, given the lack of context in different situations. But with just this sentence, we would expect that she would be more likely to be associated with the doctor, just with the lack of context. But our model actually predicts that this should be mapped to nurse, and we could assume that the model has learned some structure in the sentence, and it associates this for whatever pronoun appears there. Because in that case, it has understood the sentence and is not making associations based on gender. But that's not the case actually, because if you just flip the pronoun, it gets mapped back to doctor. Now, what this is telling us is that with different levels of specificity, we are able to measure bias in different ways or understand how bias propagates in different ways. And of course, there are still lots of questions to be asked here. What if we provide more context? What if we have more randomization of what we present to the model? Or what if we add more text so that the model actually sees more real world like examples? And these are very important questions to ask. And that's definitely something to be considered. And we have found different levels of robustness for each of these measures, or the entire spectrum of measures. And that's a line of work that I'm very excited about. And I'll be happy to talk about offline about some ongoing work I have in it. But what we need to do at this point, before we go deeper into any of these measures, is to take a step back and think about the pipeline itself and where is it that we want to intervene. Now, intervention here means two things, and we'll go into both of these. One is that of debiasing, but the other is of bias measurements. And both of these go in tandem. They always go together in trying to go through the pipeline and understand how we can intervene meaningfully at different points. So where does the bias come in from? If we ask that question, the data, of course, is a very obvious source because we scrape real world text, which has seen a lot of historical skews. So for example, let's say we have a country which has only seen male presidents. That is not a comment on whether somebody identifying with a different gender can or cannot be a president. But these are historical skews, and while our language evolves much faster, our models are more reliant on the history. So that in itself is one disparity that shows up in the representations. However, the representations have also been known to show a lot more bias as opposed to that in the data. So our modeling choices definitely have a lot of contribution to the net amount of bias seen, and they have been known to amplify it to a large extent. This makes all of these 3 points very important to assess for biases and also intervene to mitigate the same. But one thing to think about here is how accessible are these points? So the data can be extremely large and the modeling choices or the model itself can be very expensive to train. And that makes both of these points quite inaccessible to intervene at, especially when you think of debiasing. That becomes especially true when we acknowledge the fact that bias is not a static sort of fixture. We don't have one definition for what bias can manifest as. And it can change based on location, on language, on so many different factors that we need a method that is adaptable and that can be cost effectively applied. So that is why the representation stage is where often a lot of different intervention methods and strategies are applied, whether related to debiasing or even for meaningful understanding of how much bias there is. In addition, as we move forward to the user-facing application, more and more points come up where we can intervene, because as we know in NLP, we don't really go from representation to the user. There are many layers in between, and all of these are points at which we can understand how bias transfers or travels to an actual experienced harm. So we won't go into that part as much today because it's more dependent on a lot of different individual applications. Today, we'll focus more on a little bit of generalizable techniques. So let's think about mitigating biases. Now, as we said, at the representation stage is where they're most accessible and they're most cost effective, but they come with their own drawbacks, which is that of they do not have that interpretability. We do not know where exactly the bias is to be able to mitigate it meaningfully. So our first challenge is to identify different concept subspaces. That is one challenge in itself. But secondly, when we try to mitigate bias, we have to do it without perturbing any of the extraneous information. We cannot reduce bias at the expense of like losing out on meaningful information. And that has to be a balance that we consider. So let's go over some aspects of this. Identification of concept subspaces, actually, there are different ways of going about doing it. I'll just go over one very basic method, which is that of taking groups of words which are most aligned statistically with these two groups that you're trying to work with and find a stereotype between. Take the normalized difference in means, and that gives you the direction of bias. But we do it in a very iterative way so that we come to a weighted average. The reason why we do that is words are used in very polysynous ways, and they contribute to bias in very distinct and different ways. So our resultant subspace has to reflect that. So the way we do that is that we first define, let's say, some measure with which we're defining harm. And let's say we have an ideal debiasing function. Then the ideal subspace is the one which minimizes the net amount of harm experienced when using the debiaser. So what would typically happen is that we would go through different iterations until we find the appropriate subspace minimizing the harm. Now this assumes that we have the debiasing function at hand. So how do we find that? So I'll go over some common debiasing approaches. Linear projection, which we proposed back in 2019, was one of the very simple approaches that was adapted in many different ways. What it did was, given a word and a direction of bias, it finds the projection along it and then removes it from the embedding of the word. It does this uniformly for every single word, thus reducing the dimensionality and thus reducing the bias as well. However, as we can see, the very clear drawback here is that we have lost out on that entire direction. So this could have been a difference in, let's say, binary gender, or a difference in nationalities, which also encodes meaningful information and needs to be retained, which we have lost by this method. So there are variants which try to counter this. Hard debiasing, for instance, also does linear projection, but the way it counters it is that it does not debias a large list of words. Like the points in blue here, it leaves this as is. More recently, iterative null space debiasing, which is a much more aggressive form of linear projection, wherein it finds a subspace, removes it, then finds another subspace along the same sort of concept and removes that as well, and keeps doing it until a certain threshold is reached, does something very similar, but it also retains information by having this list of words. Now, while effective to some extent, there is a big caveat that you have to have this pre-provided list. And that can be very difficult, especially when you think about the extent of vocabulary. We have hundreds of thousands of words, at least, which are quite frequent and which need to be considered. And it's not really possible to have a list of all words which may or may not have been used in a biased way to go and sort of segregate in this way. So we need our model itself to be more aware of this fact. So keeping this in mind, we proposed OSCAR, or orthogonal subspace correction and rectification, which acknowledges the fact that biases do not lie along an individual identity axis. It's not gender itself that is bias. It is when it has an interdependence with a secondary subspace with which it should have been independent. That's where the bias lies. So for example, let's say we have occupations and binary gender. They should not have ideally any interdependence. They should be independent of each other. They should be orthogonal to each other. But because of underlying text, because of all the biases it has seen, it is not that way in the embedding space. So what we proceed to do is orthogonalize it. And the way we do it is that we first identify these two subspaces, then we define a new basis. So the dotted line for occupations is where it would finally lie. And this orthogonalization thus enables any point along each of these two axes to be thus forced to be orthogonal. So if we imagine there were points along the red and the blue axis, they are now orthogonal. But of course, no points actually lie along any axis, right? So they're all distributed in the space. So for any point in the embedding space, what is actually happening is that it faces a graded rotation. For the components it has along these two directions, those two are actually orthogonalized with respect to each other. The graded rotation takes place in this two-dimensional space of their components along these two directions. So everything beyond it is kept as is. So we're not losing out on any extraneous information. At the same time, within this subspace, it's only the components along, or the components along each axis are, or the meaningful part is thus retained. It's only the part that was in between that has been nullified. They've basically been made orthogonal. So this is telling us how to reduce a stereotype, a specific stereotype, instead of removing an entire direction in the hope that we are able to reduce bias generally. So this brings me to the other aspect of bias interventions, which is that of building measures, because until we have those, we don't really know how meaningfully we have been able to mitigate any bias or make any changes. So broadly, they can be divided into two groups, that of intrinsic and extrinsic measures. Intrinsic are at the representation level, and these could be the earlier methods like wheat, for example, but they have been known to be severely disconnected from actual experienced harms, which is why extrinsic or task-based or application-based different methods are more preferred. What we proposed was using NLI as a probe for bias because it's somewhat in the middle. When words have these associations that are problematic, they are more likely to make inferences that are problematic. So it's somewhere in the middle of being close to representations, and it's also a task. So what we have here, like I spoke about earlier in the slides, is that we have these pairs of sentences. We have a premise and a hypothesis, and we have to determine if the hypothesis is entailed, contradicted, or neutral to the premise. Now, we have these two pairs of sentences, and both ideally should be classified as neutral. What we find, however, is that while the first is entailed with a very high probability, the second is contradicted with a very high probability. So what this is telling us is that just the change of one word, the gendered word between these two pairs of sentences, has changed the decision. And each individual pair, in fact, even without any other context, should have been classified neutral. And if humans were to categorize it, that's what they would give, right? So there is something sinister. There is this underlying assumption that the model has made, which is getting propagated here. And this emphasizes that we need to grow out this measure in a very systematic way, rather than cherry picking few sentences here and there. So for that reason, we expand on this by using a simple sentence template and varying it in different ways to get to a more coherent measure. So we would vary the verb and the object first to get a sentence, and we vary them by using these buckets of words we have for each of them. And they always are combined to make a meaningful sentence. So we would never have something like, the doctor ate a car, for example. So then we vary the subject in two distinct ways. We have either we'll have a stereotypical word or we'll have a gendered word in this specific case, or we could also have, let's say, an adjective and an ethnicity related word or a gendered word. Whatever the stereotype is, we would change it accordingly. And this would give us a pair of sentences, each time which should be classified as neutral. And the probability with which they are not tells us about the amount of bias there is. So there's an inverse relationship of sorts between the amount of bias and the neutrality observed. We generate about a few 100,000 of these sentences using these different groups of words for binary gender versus occupations. And we also do the same for nationality and religion and polar notions of good, bad, evil associated with different nationalities and different religions. On top of these sentence pairs now, because we have these large quantities, we can have robust metrics made. We have net neutrality, which is the average probability of the neutral label across all sentence pairs. And we also have the fraction of sentence pairs that should be neutral, both of which should be close to 1, ideally. But the further they are from 1, tells us about the amount of bias there is. So if we just look at how we fare for gender and Roberta, the first row is the baseline baseline. So that's without any debiasing. That's the absolute Roberta model. If you look at the first two columns there, the net and fraction neutral are quite poor. They're below 50%, and that tells us about the amount of bias. The significance becomes important when you look at the last two columns. So this baseline was trained on SNLI data, and on the Dev and test sets, it's doing well. The confidence thus is high with which it's making these biased predictions. When we do any of the debiasing methods, hard debiasing, linear projection, INLP, and OSCAR, we see improvements. And with linear projection, we find the best improvement. And what this is telling us is that it is making meaningful progress when we just change the representation level. So it's important to keep in mind that we haven't changed anything else. We haven't changed what we train for the task, which is, of course, another important aspect which brings in bias into the system. We have just changed the representations, and we're able to move it in the right direction. But at this point, it's also important to note that none of these scores in the Dev and test columns have actually degraded in any way after doing any of these measures. But does that tell us if we have retained meaningful information? Actually, it does not, because accuracy on standardized test sets is not equal to information retained. So if we go back to thinking about our debiasing strategies, what we were doing is altering this identity axis. But when we test using these different measures, benchmark data sets, they're much broader. They're looking at, for example, SNLI data has some accounts of videos and descriptions based off of that. So it's not focusing on, for example, gender information or whether important or meaningful gender information has been retained. So it does not actually tell us if we have done like our debiasing without destroying any meaningful information. So there is a need to build measures even for that to meaningfully attribute if we have made progress in the right direction without losing out any meaningful information. So one measure that we propose is something very similar to what we proposed earlier for bias, wherein we take the same template, we fill out these sentence templates in very similar ways for verbs and objects, but we vary the subject a little differently now. We put in a gendered word, both for the premise and the hypothesis, but we do it in two ways now for the hypothesis. We have a similar gendered word and a differently gendered word. So that gives us two lists, one for entailments and one for contradictions. And both of these should be high. So if these probabilities overall or these metrics give us high scores, that tells us that we have been able to retain information. So taking this as an average, I have this plot now to tell us how we fare in general with our debiasing strategies. So on the y-axis, we have the average entailment and contradiction scores on the meaningfully gendered test. So higher the value, better the retention. And on the x-axis, we have the neutrality score, which is the amount of bias removed. So higher the value here, better the debiasing. What we have now is that we can see that linear projection has reduced the most amount of bias, but it has also lost out on a significant amount of information as compared to the baseline, which is without any debiasing. INLP has actually retained a lot of information, but it has also not debiased anything significantly. OSCAR is about optimal, but it also has reduced some amount of information. So what this goes to show that depending on the application, depending on different scenarios, we would get to a method that suits us the most. So for example, if we want to be most aggressive at removing bias, we probably don't care enough about the gender information for a given task. Maybe we want to select a more aggressive method, but if we care more about retaining information, then we want to select otherwise. So what this goes to emphasize is that debiasing is not a one-size-fits-all sort of solution. We have to consider the bias that we're working with, the language that we're working with, the model, the language representation, and a lot of these different factors. And think about this trade-off when we're trying to select the appropriate measure. Often we focus more on one axis over the other, and that's with different communities prioritizing different things. But we want to think about all of this in tandem to be able to come to something meaningful, which helps us have both efficiency and accuracy and also less bias.
A quick question.
Yes.
So, do the standard data sets not have any of the gendered instances? Like, why is it equally accurate on the standard data set?
It doesn't have any. So it's not asking. So standard data set will have like sentences like, the girl was holding an umbrella, and then the hypothesis will be the umbrella was pink, red, blue, something like that. So it's never about meaningful, say, identity-related information.
I guess the other way to ask this question is, do you think there is any other information gained that somehow is not being measured by doing this sort of debiasing?
Information gained by the model?
Yeah.
During debiasing?
Yes.
Gained and not lost.
Yeah. Like somehow it's a better model of how it should be. So maybe there are other consequences that we don't.
I would say that's possible. I mean, we're not losing information is all we think about, right? Like we're trying, because we're essentially the way we alter it is with the goal of removing a specific kind of information. So I think the push definitely is more towards understanding if we have lost. Gaining, maybe there is a structure that we have gained that is better. I do think that is potentially possible and should be explored, but yeah. Like gender information in general clusters better after debiasing, but a general statement about all types of dimensions is something that's hard to predict. Yes.
So for your x-axis here, this neutral task,
yes.
Are you just testing on like, you said you defined like a set of subjects that you were using for instance, the binary gender task, right?
Mm-hmm.
So like a set of subjects that you're testing with different genders. I missed whether you have like a held out set, an evaluation set for this metric that you're calculating.
So we only develop a test set. That doesn't go into training at all. We train on SNLI data, the standard data for like training an NLI model on.
Yeah.
And then we test on this.
So what do you use for removing the bias dimension?
We have a held out set of words. So let's say it's gender, then we have a held out set of gendered words that we use to train the subspace or to do the debiasing.
Yeah.
And then we have a different set of words which would be used to generate the
this metric.
This metric.
Okay.
Yeah, that's a great point. Yeah.
Another question, I guess I feel like the range of the x-axis here is pretty, I mean, it's big, but it's not like the bias problem is not solved.
Absolutely.
Right? So just to be clear, I think you expect it to be close to 100?
No, because we are only changing the representation. So the pipeline comes back. The bias comes in from a lot of different aspects, and we are focusing on one aspect and trying to modify only that point to see how far we can get towards this ideal. That would come from, like, I guess, a lot of collaboration on all of these fronts, like having a better trained model which encodes less bias, having a data that's cleaner, having an application. So even for NLI, it has these cues, like pronouns and the distribution are really disparate. Mm-hmm. So even cleaning that is important. So for example, for multi-NLI, when we actually train on that, we get a much worse score. So training on the training data set is also very important.
So I guess you're saying that the SNLI training data also has bias.
Yes.
Of the sort where doctor and woman to say.
Yes.
Entity.
So there are a lot of different factors that are coming together. So this is with the focus on just one aspect and trying to modify only that and nothing else, and seeing how far that can take us. And hopefully when we do this for every individual component, we'll get to a better sort of collaboration or a chain of events, which can eventually reduce bias much more significantly.
So yeah, so I was wondering, like optimally you'd like all of this x-axis to be at 1, right? So because I guess I'm wondering if you so your baseline here, I guess this is what I'm wondering. This baseline that you're using is the without any kind of bias removal, yes. Right? And so it's getting a neutral score of like just over like 0.35, right? Mm-hmm. And so we're getting an improvement of that much. Okay. I guess I'm wondering, like, if there's a limit that you could get with this model on the x-axis, if you're like close to that limit, or if there's a lot further you could go, just with within the representation, or if there's some way of like creating a baseline to measure that.
So that's a great question, and I wouldn't have a direct answer for it, partially because it also comes down to how you're measuring it. Because how you're measuring it also tells you about how far or what ideal debiasing can look like. So for example, iterative null space projection has been known to be very successful at debiasing context-free embeddings. But even there, and it's removing like about 35 dimensions out of a 300-dimensional space. But even there, you don't really get to the optimal point or the one in whatever measure that they're trying to get to. So it's like the limit is not well understood of how far you can go. That I guess is the best.
I guess if you like did this same task with the baseline, but with non-gender stereotyped words, and saw what the neutral score was for the work of those. Does that make sense? Like that's kind of subjective. I don't know if it's the best metric, but like if you took subjects that aren't generally like associated with the stereotype or something, and use those to get like to see how well the model is normally getting
how central it
scores.
is to both stereotypical and anti-stereotypical of sort words.
Yeah, and it's like so that could kind of give you an upper bound or something like that.
True. But, so this does take into account both, right? Because you're varying all words with everything. So it has all, for instance, it'll have doctor with all possible gendered terms. So if getting to a balance would also mean getting closer to one in some sense. But I could see the like also like ultimately doing the ratio in some sense.
Yeah.
Thank you. I believe you had Katniss.
Yes. The goal of these methods is to create some kind of unbiased representations, if I got that right?
Yes, mitigate the, yes.
Yeah. And I guess what I wanted to ask is like, usually we will use these representations and fit an additional layer afterwards, or a few additional layers afterwards that might themselves during training, because they are task specific, introduce some bias. So I was wondering, like, it's one thing to measure the effects on bias in the representations, but that doesn't necessarily guarantee that the final model itself will be unbiased. So I'm curious to know if there's like, what are your thoughts on that, and how do you see this kind of strategies being applied and extended? Because in the like the final purpose is to mitigate bias in the end tasks themselves.
Right. So just to clarify, the way this debiasing was done for Roberta or even Berg was to apply it after the first layer. So the input layer where you just have the tokenization done, that's where the thing is applied, the debiasing, and then it carries forward to the rest of the layers. So it's not at the very end of the representation where, so even that small change and having so many layers afterwards and an MLI model has actually retained a lot of this debiasing or reorienting that we have done. But I do understand that potentially we could have more complex models lined up one after the other. And that is why there is a scope to put in different intervention points at each of these different layers to understand how much got carried over and how much we can mitigate at each of these. I don't think that we can have just one step at the very end, let's say at the absolute application, where we can reduce all of the harm, because by then you have too many channels pouring into that specific output, right? So then it would be something too post hoc at that point. Like you won't get a meaningful answer maybe. So I do think it has to be collaborative at all of these different levels to get to one sort of meaningful output. Okay. So while this actually sort of emphasizes what I'm trying to get to, that we have to always make all of these different considerations and how complex this problem is, it also gets more complex than this. Because so far, whatever we have discussed, these were simple terms, because we considered one identity, one sort of stereotype, and we assumed that we could make all of these sort of measures and all of this. But that need not always be true, because biases are much more complex than this. Whatever we've called bias so far has just been an individual stereotype. even for gender bias, it manifests itself in much more than a binary gender versus occupation stereotype. And that is all we have tried to account for. And even there, we have a lot of snags. So for example, a person has much more than just one identity. They have intersectional identities, they have multitudes of identities, and all of that does not always interact in additive manners. The net bias faced by somebody who is in the middle of two minorities is much more than a compounding effect, and it's not even linearly separable. You cannot measure these biases separately or debias them separately. They have to be done in conjunction, and that is not really well understood, or it's not even generalizable across different types of intersectional biases. Then we have made this very broad assumption that we can actually have discrete categories within identities, and that does not translate into real world as much. So we can have non-static and fluid demographic identities, and that needs to be accounted for somewhere in our modeling process. Bias can also look much more than just a stereotype. It can also be the lack of representation altogether. And that is a much more complex situation to try and measure, because it's not about having erroneous representation. It's about how do you actually measure a lack of representation. And finally, when we think about biases, we have a very Western and English-focused perspective, and that needs to expand much more, because we are grading models as usable across the globe after checking it for biases with only a Western perspective. And that is severely limiting when we think about how we have expanded into multilingual embeddings, which are learning through like different modes, different languages, and yet we have a very limited focus on what it can look like across different regions. So let's talk about some of these aspects, specifically about gender inclusivity in NLP. Now, why this is important is because gender is something that is very entrenched in different tasks within NLP, and gender bias is also one of the most widely studied types of biases. However, what we understand as gender and what the languages understand as gender can be different, and it actually can be quite narrow. So this is the task of co-reference resolution, as we have seen earlier too, and if we give it a simple sentence like this, our model is very easily able to understand that he refers to Alan in this sentence. But if you just switch the word he to they, not only does it not resolve it correctly, it doesn't recognize it correctly either as a pronoun to be resolved. So this in itself is a harm, and we can see how it would plug into different applications. But let me talk about a very specific use case. So with the Department of Public Health at UCLA, what we were trying to do is use this data set called the National Violent Death Reporting System by CDC, which is records of homicides and suicides. And there's an effort to automate retrieval of documents that are similar based on the accounts and the people involved, and understand the chart of who was affected by whom. And as a result, maybe flag people that are at high risk or understand scenarios. But even here, our models actually falter. And these are data sets where self-identification of gender and sexuality are both low, extremely low. So in such cases, when our models are unable to resolve properly, we can see how we amplify the bias and end up propagating marginalization of already marginalized communities. So this is extremely important to think of. And so we went into the process of thinking about how this goes through the pipeline. How is it that we end up with such severe skews and such misrepresentation or underrepresentation? Of course, the data does have a large skew. It doesn't have a lot of representation, as we would expect, because there are historical usages of pronouns, for example, that we would find common or uncommon. So just looking at Wikipedia, we have he being used significantly much more than any other pronoun, and she and they about the same times, but they has been used much more in a plural sense. So we went in and we actually annotated a lot of the usages, and we extrapolated, and it was less than 1,000 times or so. Z and say have been used a few thousand times, but not as pronouns, of course. They have been used as acronyms for companies or Polish words, but rarely as meaningful words. And we would expect this somehow, right? Because the text is historically going to be skewed. And this skew gets represented in the language models that we built. So this is GLOVE, and before we read this, we should remember that nearest neighbors was almost considered a gold standard when context-free representations were common, to think about if they were embedding information meaningfully. So these are nearest neighbors of some pronouns, and we see that indeed for he and she, it is embedding it meaningfully. But the same cannot be said for neopronouns. Now, it's not like no non-binary pronouns or words were embedded at all. They were embedded meaningfully. So for example, trans man and trans woman are sort of embedded meaningfully. But if we go back to the stereotype that we have recreated several times over for binary gender, man is to woman is to doctor is to what, we find that we cannot recreate the same for trans man and trans woman. They were actually not associated with any occupation words at all. So that tells us that the stereotype that we have been working with and calling gender bias is not really an all-inclusive sort of bias for gender. It can manifest itself in so many different ways where some gendered words are not related to occupations at all. There are also additional stereotypes that are there. So for example, there are actual different degrading words which are associated or colloquially used slang words, which I have left out of the slides because they're potentially triggering, but they have been associated much more with non-binary gendered words. So it's a two-edged sword of sorts. Either there is bad representation or a lack of representation. And we might expect this out of representations like glove because they're not known for embedding rare words as well. But the same is also seen with bird, for example. So we tried to see if there was a general understanding of a singular versus a plural pronoun. And that seemed to fail when we tried to disambiguate between its understanding of they in its singular form versus they in its plural form. So what we did was we trained on a set of sentences using I and we, and then we extended to the situation where we had he versus they in plural and she versus they in plural. And of course, it was able to disambiguate well there, but that falters when it tries to disambiguate between they singular versus they plural, even after fine-tuning over a large set of these sentences. So a general understanding of what pronouns can look like is something that is lacking, and that gets reinforced when we see how it can actually lead to active misgendering. So we created a lot of templates like this, and we vary the name out of this list of names that we have from SSN that are least gendered statistically. We fill in the pronoun in the first sentence ourselves, and then we ask the model to fill in the one that has been masked. So when we put in his, we find meaningful completion. When we put in her, we also find meaningful completion almost at the same level. But that stops being the case for other pronouns. And in fact, it then predicts he instead of the respective pronouns. So it is not just not predicting the correct pronoun, it is also misgendering by predicting a wrong pronoun. Now, we can imagine lots of reasons as to why that would happen, because pronouns are something that is well understood, but it's been understood in a very closed way, such that rare words which are used as pronouns are not really imbibed into this understanding. And the reason, yes?
Sorry, quick question, maybe a clarification. So when it is they that fits into the mask, should it be were or should it be was?
It was were. We switched that. This has been just.
So when you put were, what was 0.52? Was that accuracy or the probability?
That is the accuracy.
So what else was it suggesting? I guess I'm curious if you put a were.
If you put in a were, it was suggesting. So it was suggesting he still actually.
He were feeling sick?
Yes.
Interesting.
It was a very high probability of he, no matter what we put, even though we've selected names in a way that it was gender neutral.
Right.
And so we can come to ask the question as, even though all of this happens, does this really translate into an actual harm? Because that is not something we know of. That is not something we totally understand of how that translates into an actual harm. So for that, we surveyed about 19 different groups of people actually, where they identified as non-binary, but they also had some experience with AI. And the reason why we kept that as a caveat, that they had to have had some experience with AI, is because we did not want to impose our understanding of what bias could look like onto their answers. Instead, we wanted to have a much more free-form sort of like survey where we allowed them to tell us what harm can look like when using these different tools. So we gave them different tools like Translate, NER, CoRef, demos, and then we tried to understand what they see as representational or allocational harm out of it. And with NER, they actually told us that there were a lot of names that our systems were unable to identify. For CoRef, we have already seen how it actually maps back to wrong words or doesn't actually resolve them correctly. And this we can see going forward to cause a lot of different harms. So if we look at two spaces specifically, education and healthcare, in healthcare, we know that language models are quickly being adapted to solve a lot of different tasks or to retrieve a lot of information. But here, gender history and gender identity are both extremely essential. But since we have no way of discerning between that and we are considering them as these static sort of entities, it doesn't grasp them well. And that can lead to different problems in their health outcomes or even the course of medical assistance they are offered. In education, there has also been a growth of different systems like automatic grading or grammar checkers. So for instance, we have this from Grammarly from very recent times. And I will hide this to show. It basically says correct your spelling. It's not able to identify that it's a pronoun. And there are, of course, different ways to think about this. Maybe we don't want to predict an exact word for a spot. Maybe the idea is to predict a category and then iterate over the words within that category to come to the correct word. That might be a potential solution. But as it is right now, we can see how it's going to cause harms if we just let it identify what words are to be correct based off of just the history of text that we are putting in to build the model. So this brings us to this very important question: how and if we should even model gender. So when we try to think about modeling gender, we always want to make sure that we have represented it fairly. But are we really making it fair if it is not fluid, if it's still bucketed, it has these categorized sort of entities, and it's not allowed to mutate over time? And that is one question that we as a community need to be figuring out as we go forward with these language models. So there has been some partial solutions that have been proposed to some extent. So for example, they as a third bucket has been proposed. And in our survey, we had actually talked about that too. And clearly that too is a form of misgendering because not everybody identifies with this pronoun. And neopronouns are something people actually use in their daily lives. So just having 2, 3, 5, 10 buckets is not really the solution. We need to do better than that if we want to model gender truly fairly for all in our models. There have, of course, been other approaches which try to design better data sets. Now, there's an approach where we augment the data, we do something better with maybe the test data to make sure that a model does fairly for different genders and not just for the two binary genders. But even here, there are, of course, obvious challenges because if we do it only at the representation stage, it has already learned these biases. And when we augment, are we really getting to natural sort of sentences to test for? Is that something that we can actually even achieve? So there are different questions now as a result to try and answer. So for example, maybe it's a task-based approach we want for modeling gender. What we have done so far is we encode gender information. Whatever we find in the data set gets embedded. And then if we find an experienced harm, we try to go backwards to try and remove it. Maybe we need to approach it in the other direction where we do not encode gender information. But if we have a proven or an explicit way of getting benefit, that's the only point where we explicitly provide gender instead of assuming gender from underlying data. We want to have better modeling with more humans in the loop and better representation throughout the process. So right now we have a lot of skews because the kind of annotations we have, they themselves do have their own skews based on who annotated them. And that also affects the process throughout. And finally, another thing, and this is an incentive both within Google and beyond in the community, what we have seen is that we need to have better data documentation. We need And this comes at the stage of building the models. So whatever data we're using, we need to communicate better about what data has been used. We need to have better notions of the provenance. So what are the sources for the data? What timeline was it taken from? The distribution. So what words were most frequent? What were the associations or co-occurrences? We need to have a data-first approach where we go in, we see if something was used frequently in a given region in a pejorative manner, and then go and record that and try to see if that comes up as bias in the embedding on the representation or subsequent model, rather than going towards the model in a more blind manner and trying to work our way backwards. So I think I'll stop here at this point, and I'll take any questions you have.
Any questions in the room?
Yes.
So do you think, like, with this smart human in the loop in the annotation, I think whatever you do, you will have those biases that are based in people. Like, all the text we get for language modeling from internet are really bad in this stuff because people have these biases. So how should we select those annotators?
So there is a very good body of work, actually, at least growing now, talking about the diversity of annotators that is needed, or that is at least sufficient in some way to get to a good data set. So for instance, some questions to think of, especially when we talk about bias or offense, is if the same annotator is bilingual, would they consider the same word to be equally offensive in both languages? Or even if it's the same word, if somebody is bilingual versus unilingual, do they see it differently? So there are a lot of different questions to be asked to get to good annotations. But I guess the short answer is that yes, currently the annotations we do have a large amount of bias in the annotation process itself. And there is a lot of work needed to get to that point where we can have a much better set of annotations. But gladly, I think there is a push of late towards that. So hopefully we will get to a better answer of if we can have a better representation in that. Yes.
So the examples you gave at the beginning of the talk, where you do treat gender sort of in a binary, it's clearly not solving the sort of deeper problem because it's not a binary for a lot of people. But is there a sense in which solving that misspecified problem is that helpful but not good enough? Or is there a sense in which that could actually be dangerous or negative towards the broader goal? If that makes sense. Like, does implementing these fixes on the binary have any adverse impact on a more fluid definition of bias?
So are you talking about the measurements or the debiasing strategies?
The debiasing strategies.
So the reason why it does not have a bad effect is because those representations are not even around those subspaces. And since the goal is to protect everything else, it stays. So it's not explicitly harming it. The way it would harm it is if we say we have corrected for all gender bias by doing this. So for example, if we use binary gender to define the entirety of the gender subspace, then that's where the problem would lie. But if we explicitly say we are covering the binary gender, or we explicitly find the binary gender and we want to reduce a specific stereotype, then we are not harming anything else, if that's it.
Yes, it does. So in that case, the danger would be in overpromising and people interpreting the output of the model as
that, and also trying to maybe capture subspaces, for example, going back to that very specific example. So if you use a wide variety of gendered words, which have very different frequencies, as is the case, and you use all of it to capture one single subspace, then the binary gender will dominate what you capture, and anything that's infrequent won't really be captured. So even though technically you've used everything, right? And you've tried to reduce the same stereotype for everything, but it won't actually follow through because one is significantly much more dominant in the space as opposed to the other.
Maybe I'll ask one more question. This is at a high level, right? So essentially, my language models don't seem to be biased, is because they're trained on historical bias data. And I feel like human in the loop
is kind of trying to address that,
Mhm.
because presumably human in the loop is more modern set of biases, right?
Mhm.
It's still biased, but they are more acceptable in 2022. But it still feels like by the time language models get accepted, the world may have moved on, and depends on who is the human in the loop. There are plenty of people who are still not subscribing to the same stuff. So it feels like a whack-a-mole kind of approach, however you think about this, whether it's from the training distribution point of view or from getting the right humans. So yeah, how do you sort of foresee this getting solved if the language is going to be evolving over time anyway?
I totally agree. I do think there needs to be speaking just about gender, I think there needs to be better communication with gender studies. But overall, I think even though the slide is called How and If to Model Gender, I think this follows through for most demographic information, because most of them are actually fluid and are actually much more than these individual buckets we have. So to some extent, I feel it should be a task-based approach more than anything else, where we need to have an actual benefit for using the information rather than using it generally and then removing it. So for example, right now, any credit profiling sort of algorithm doesn't really use any explicit information about gender or any other attribute. And that's because they have explicit variables. And we are not able to do that with language because it's so distributed. But ideally, maybe that is what we need to be controlling for, where we don't let gendered information through unless it has to be a categorical variable supplied somewhere instead of something that's assumed from underlying text. That is one way how I foresee a solution. That is maybe not the ideal solution or the only solution by any means, but potentially one of the solutions.
I see. So there should be no implicit inference
of demographic information.
Yeah. That's interesting. And how to get language models to do that
Is another sort of.
Okay, I like that. All right, let's thank Sunipa again.